Good day, everyone. I'm Joan Schmeltz from USRA, and it's my pleasure to introduce our next plenary lecture. Dr. Elisabeth Mills is an assistant professor at the University of Kansas. She studies the center of our galaxy, specializing in observations at infrared, millimeter, and radio wavelengths. Her research focuses on physical, chemical, and dynamical processes responsible for molecular gas conditions in this extreme environment. One of the most important jobs of an AAS vice president is to invite plenary lecturers. In my mind, these should be engaging speakers talking about compelling science. When I heard Betsy give a talk at the AAS meeting in Denver, I knew I wanted to issue my first plenary invitation to her. It took us a couple of tries to get the timing right, but I'm so glad she was able to accept the invitation to speak to us today. Betsy studies star formation at the Galactic Center and has recently begun high-resolution surveys of the gas in the nuclei of nearby galaxies. With these data, she hopes to better constrain the inflow and outflow processes that shape nuclei and the galaxies as a whole. Today, she'll be our tour guide as we journey to the center of the galaxy. Will everyone please join me in welcoming Dr. Betsy Mills.
Thank you so much, Joan, for the introduction. I'm extremely excited to be here to tell you about the center of our galaxy and to give you a close-up tour of its structure and its contents. But I also want to acknowledge the incredible privilege so many of us have to be focusing on astronomy today. And so I ask you all to take a moment of silence to remember Ahmaud Arbery, George Floyd, Breonna Taylor, Tony McDade, and so many others who have died at the hands of police violence. And consider as you do how racism is present in academia as well, and think about how we can better act in solidarity with our Black colleagues and students, many of whose hearts and minds are elsewhere as their communities and families grieve. And acknowledge while you are doing so the absence in our midst, the lost Black students and potential colleagues who never had the chance to pursue their dreams of science because of the toll that police violence and racism continues to take in our country. So we all live together inside of the Milky Way galaxy. This is a relatively normal and quiet barred spiral galaxy. And our sun is located in a spiral arm on the outskirts of the galaxy. But today I'm going to be focusing on the very central regions. And these regions are approximately 26,000 light years away. And that means that every photon that I will show you today took 26,000 years to travel all the way from this central region to reach the detectors of our telescopes. And this is a fantastic distance. We can't hope to travel there to take close-up pictures, let alone collect any samples. And yet it isn't necessarily as far away as it seems, because we believe that all of the physics that happen in these tiny central regions have an outsized impact on the surrounding galaxy as a whole. So how do we know this? Well, we know that the center of our galaxy, like all other galaxies, its size and larger, hosts a supermassive black hole. And when we look at other galaxies, we see that when we look at the size of their supermassive black hole, it correlates with galaxy properties on much larger scales, specifically the mass of the galaxy's bulge on kiloparsec, or 1,000 of light year scales. So while it's not clear whether this is just correlation, the same processes lead to building up a black hole and a bulge, there is some good evidence that suggests that this relationship is actually causal, and that the black hole and its processes of growth can shape the surrounding galaxy. And we see this by looking toward the centers of many of these compact but extremely massive black holes, which are responsible for launching huge jets of relativistic plasma and particles far beyond even just the center of the galaxy, all the way out into the space in between the galaxies themselves. And this huge eruption that you have coming from these black holes, this potentially galaxy reshaping energy, this light display and these enormous lobes of plasma, these originate on scales so incredibly small. You're looking now at the beautiful image of the black hole from the Event Horizon Telescope in the nearby galaxy M87. These originate on scales so small that this event horizon is comparable to the size of our own solar system. And so from this, we can get an idea of the fantastic range of size scales that are associated with galaxy centers. In just this example, you see you have over 6 orders of magnitude in scale, from the central black hole all the way out to the size scales that that tiny black hole can influence. But I want to bring the focus now back to our own Milky Way and exactly what lurks in its central regions. So of course, living inside of our galaxy, as we do, means that we never actually get to look at it like this. So instead, what we have to do is we have to peer through all of those 26,000 light years of the disk and the gas and dust in the disk in order to see through the center. And our view looks something like this from the Earth. Now, this also means all of this gas and dust that you're looking through, it means when you look toward the center of our galaxy with optical wavelengths, the sort of visual light we're used to using to detect the world around us, you see this, which is a whole lot of nothing, or at least nothing that actually comes from the galaxy's center. So if you want to actually study the central regions of our galaxy, this forces us to move to different wavelengths. So either longer wavelengths or more energetic wavelengths like X-rays and gamma rays. So here we're going to push on to longer wavelengths and use these to pierce this veil and look through this gas and dust and start to look toward the center of the galaxy. And even just at near infrared wavelengths, what you can see is that we're looking at the right place. This definitely is the galaxy center, right? And this is a bright region, a concentration of stars, an energetic powerhouse of our galaxy. Now, to fully see through this intervening veil of dust, we're going to keep going all the way to the mid-infrared now. And now you can clearly see, sort of unobscured, the center of our galaxy in some of its glory, the central concentration of stellar energy that's being reprocessed by the dust that is there. Now, at mid-infrared wavelengths, these are sufficient to really pierce and look through all of the gas and dust in between us and the center of our galaxy. But the gas clouds in the center of our galaxy are so thick and so dense that many of the clouds in the center of the galaxy we still can't see through. And these show up as infrared dark clouds. You see them silhouetted against the background emission. And so we have to go to yet longer wavelengths here to actually see the zone in which these clouds dominate. So this is our first big stop on our journey to the center of our galaxy. This is a region known as the central molecular zone, and the location of our central supermassive black hole here is marked with a cross. The orange emission is thermal emission. This is coming from the cold dust in these incredibly thick and dense clouds. And even if these blobs of orange emission look a little bit unremarkable, each of them actually contains 100,000 to 1 million solar masses worth of molecular gas. This is a huge reservoir of molecular gas, and this is the reason that this region is named the central molecular zone. Now, although we cannot directly get an optical or an ultraviolet view of what's going on in this region, the long wavelengths that you see in this composite image, infrared, radio, and millimeter, are actually able to tell us a fairly complete story of the stars in the central regions of our galaxy. So moving to radio wavelengths now. So this is a beautiful image from Meerkat, a pathfinder instrument for the upcoming square kilometer array. And at these wavelengths, what we mostly see are the impact of past generations of stars. So we can see shells of magnetized plasma, the remnants of former stars that are now dead in enormous supernova explosions. We also see incredibly mysterious and fascinating features. We see evidence of extremely high energy phenomenon causing these magnetized gas filaments that you see largely running perpendicular to the plane, which appear to pervade the center of our galaxy, although we're still not entirely sure what leads to these. Now moving from the radio now to the infrared, and what the information we get from the infrared. Now what we see is a region that is lit up by the stars of today. So this is a composite image from Spitzer, from Herschel, and especially from the Sophia Observatory. And we see here the impact that current stars are having on their surroundings. They're heating, they're ionizing, they're disrupting all of this surrounding gas and dust. We also can see here some evidence of massive young clusters of stars in this region. And here we see some evidence that the environment in which stars form in the galaxy center, an environment that's very different from the disk of our galaxy, where our sun formed, this may impact the nature of the stars that form. So we see in these clusters a possible deviation from the initial mass function, or the standard distribution of masses at which we believe stars and stars in a cluster are formed. It seems like these clusters may be a little bit overproducing some of the massive stars that are present in the center of our galaxy. Now moving on now to millimeter wavelengths. Here we see what for me is the most exciting component of the stellar life cycle. These are the tens of millions of solar masses worth of gas that are the future of the center of our galaxy. These represent the potential for future star formation, as well as future fueling of the central supermassive black hole. And this incredible amount of gas crammed in this tiny region experiences an environment like you see nowhere else in our galaxy, and it very much shows when you look at the properties of this gas. So if you ask, what is this gas like living so far in toward the center of the Milky Way, you see that it's several orders of magnitude more extreme than gas anywhere else in the disk of the galaxy, based on almost any indicator you choose. So you can look at gas density. And what you find is the gas density of these clouds on average ranges from more than 1,000 up to 1,000,000 molecules per each tiny cubic centimeter. And this is compared to sort of an average density for molecular gas in the disk of our galaxy of about 100 up to maybe 10,000 molecules per cubic centimeter. We also see the gas here is much more turbulent. So on small size scales, we see typical line widths, which is how we measure the turbulence, that range from 2 to 10 kilometers per second. When you look at molecular clouds in the disk on these same size scales, you typically see sub-kilometer per second, less than 1 kilometer per second line widths. So it's much more dense, it's much more turbulent. And the other thing you see is it's much hotter. Hot, you have to be careful here, is a very relative term. So when I say hot, I'm talking about 50 to 300 Kelvin. We're talking about just barely scratching the surface of the room temperature you're experiencing right now, right? So we call this hot because if you go anywhere else in the disk of our galaxy, typical gas temperatures are sort of 10 to 20 Kelvin. So this is much, much, much warmer than the typical gas you see in the disk of our galaxy. So putting this all together, this is gas that is hot. This is gas that is turbulent, this is gas that is dense. And a big question we have then is why? What is making the gas here so different than the gas in the rest of the galaxy? And in some ways, this seems like a silly question because this really ends up being a case of too many suspects because there are so many reasons to expect that the galactic center is going to be more extreme than the disk. But we can't just be satisfied by saying, well, we know something must explain it. One of these reasons must be the reason that the gas here is so different. To really understand how galaxy centers evolve, we need to isolate the physics that is most responsible for making the gas here so different than the gas in the rest of our galaxy. We need to identify the mechanisms that drive these conditions, and by identifying them, we can then say, are these the same as the things that make gas properties different or extreme in other galaxy centers, in galaxy centers that have a lot of star formation, or galaxy centers that have an active black hole? Is our galaxy representative? Is our center of our galaxy representative of the processes that we know take place in galaxy centers? And so we can break up some of these possible variables, some of the suspects for making the gas different, into a couple of categories. And the two categories I like to break it into are to first ask, could it be just because of the destination, just because of where the gas is? So here we're saying there are a lot of environmental processes that the gas experiences, right? Whether it's tidal shearing, whether it's simply the large number of stars and the high UV background and X-ray radiation that pervades this region, or even the enhanced cosmic ray ionization rate. There are a lot of things at play that mean that gas, just sitting by virtue of sitting in the center of our galaxy, might be expected to be more extreme than gas elsewhere. But we also know that the gas in the center of our galaxy has not always been where it is today, at the galaxy center. So various processes, including the sorts of processes that act inside of the galaxy, independent of mergers and external accretion, can act to funnel gas to the center of a galaxy. And this funneling process, the resulting shocks, the loss of angular momentum, the release of energy as it travels deeper into the potential well, these processes may start to fundamentally change the gas properties and continue to change it, right, before it even arrives at its destination. So to isolate the most important variables that are at play here in making the gas extreme, and to investigate whether the journey or the destination is more important for shaping the gas, we have to follow the gas even further in to the center of our galaxy. Because, speaking of the journey, we still haven't made it all the way to the central supermassive black hole. So we're going to move back to the center, and we're going to move through the central molecular zone and go on to smaller size scales. Now, one difficulty that we encounter when we study the structure in the center of our galaxy is knowing what the true 3D position of this gas is, because we're stuck seeing the center of our galaxy edge on. What we know, however, is that just looking at the motions, studies of the kinematics of the gas, that almost all of the gas we see, 99.9% of the dense gas we see traced by the orange emission in this image, actually appears to lie on a ring, with all of this gas lying at a radius of at least 300 light years from the black hole. So we have to be a little careful here. So I'm going to start zooming into the black hole, right? And so this now is a radio image. Now we're focused on the central 20 light years, or what appears to be the central 20 light years. Because in fact, we believe that while it looks like we have a huge supernova shell, we have a couple of smaller shells, 4 smaller shells coming from O stars, well, this looks like evidence of star formation within 20 light years of the black hole. In fact, the appearances are a little bit deceiving. And we believe that most star formation that's occurring in the center of our galaxy is all happening at least 100 to 200 light years away from the black hole. And these sources of current and past star formation are likely in front of the black hole by at least 100 light years. But we'll keep going here. And so now we're going to a gorgeous infrared image. This is another image from the SOFIA Space Telescope. Now here is some gas that we know based on its motions, this is a really gas that is really within 10 light years of the black hole. So in the far infrared, we're picking up some warm dust here. And this is sort of the last, this is as close right now in our galaxy as molecular gas gets to the black hole. This is the last reservoir of the molecular gas as we approach the black hole. It only contains, again, about 0.1% of all of the molecular gas in our galaxy center, about 10,000 solar masses worth of gas. And it forms a ring-like structure surrounding the black hole. In some ways, this is a structure that could be seen as analogous to something like the torus around an active galaxy nucleus, though again, remember, our black hole is not active. But unlike, and perhaps explaining why our black hole is not active, right? Once you go inside of this region, once you go inside of this ring, the amount of gas drops off dramatically. So just inside of this ring, if you go now to ask about the neutral gas, there's only a few hundred solar masses worth of neutral atomic gas inside. Moving further inside now in the radio image, this is dominated now by emission from the mini spiral. This is the ionized gas, some of the closest that gas from further out in our galaxy center gets to the black hole. This is only about a few tens of solar masses worth of ionized gas. You can also see in this image a point source that is the synchrotron emission from the supermassive black hole. We're starting to get there. Also notable at these size scales, everything here in the mini spiral and inside of the circumnuclear disk is now dominated by the gravitational potential of this supermassive black hole. Whereas outside of the circumnuclear disk, you have a roughly equal contribution from the mass of the black hole and the mass of the stars that are in a central nuclear star cluster. When moving into the central light year, now you see the core of the central nuclear cluster, some of which is actually quite young. Basically, all you see now is stars. And it's important to note that these stellar winds, the winds from these stars alone, are sufficient to account for the small amount of accretion we currently see on our black hole. So basically, right now in our galaxy, the gas from larger radii is not making it this close in. If we keep going, we see some really interesting evidence that even though today gas doesn't make it very close to the black hole, we believe that only a few million years ago it did. So here we see some of the young stars in the central light year and the innermost of these stars. And these are the S stars whose orbits have famously been used to determine the parameters and the existence of our central supermassive black hole. And these are part of a group of stars that are suggested to have formed in situ, where they are, in one of the most extreme environments you can imagine, an incredibly dense gas disk, right? Less than a fraction of a light year from the black hole. And speaking of the black hole, you might notice we now have to make an enormous jump to tiny, tiny scales, right? To get to the scales on which minuscule amounts of gas are currently accreting onto our black hole. And this, sadly, I will note, unlike all of the other images, is now a simulation, right? We hope in the next few years that the Event Horizon Telescope will give us a real-life look at the event horizon of our central supermassive black hole. But this is incredibly small. We've gone now to 0.00, I think there's like 6 zeros, right? Such small fraction of a light year, only a few million kilometers across. And this is the scale of the journey that gas takes. If we were to feed and substantially grow our central supermassive black hole, we have to go from these hundreds of light years down to these sort of micro light year scales in order to build up and to have built up our supermassive black hole. And so given the scale of this incredible journey that you have to take, we can ask, and to get back to this question of, is it the journey? Is it the destination, right? If the journey is primarily responsible for shaping the gas, you should see the gas properties get significantly more extreme the closer the gas gets to the black hole. Because our black hole is not active, right? So we don't expect that it's greatly influencing its surroundings at present. We also said that there really isn't inside of a few hundred light years almost any star formation going on. So in some ways, the very core of our galaxy is quite quiescent. And so we don't expect that gas would encounter a substantially more extreme environment than it already experiences at large radii. So to ask how the journey might be influencing the gas, we're now going to compare some of the properties of the gas on these hundreds of light years of scales in the central molecular zone to the circumnuclear disk, as close in as molecular gas gets these days to our black hole. So we're going to start on the large scales, and we're also going to start by looking at the gas density and looking at how it's changing as a function of radius. So to do this, we have a very special tool. We're going to turn to the molecule HC3N, or cyanoacetylene. So why this molecule? It's got a few important properties. So it's a linear molecule. Atoms all form a straight line. So it has some pretty simple transitions, pretty simple quantum mechanics. It's also quite heavy as molecules go, which means it's got pretty closely spaced energy transitions, and they start down at radio wavelengths, which makes them very accessible to the telescopes that we use. And finally, this molecule is actually rare enough, it has a low enough abundance, that we think that it is reasonably optically thin. This low abundance means that for every, say, billion molecules of H2, there are only a few molecules of HC3N. So why is it important that it be optically thin, and what does that mean? Well, let's think of a molecule as if it's a light bulb. Sort of a basic way to think about detecting the light. Imagine that our molecule is a fixed watt light bulb. And so counting the amount of light then lets you count how many molecules there are. However, if there are too many molecules present, the light can get blocked, actually reabsorbed by the molecules in front, and you can no longer use the total amount of light that is present to count the total number of molecules that is there. So in this respect, it's very important that HC3N be optically thin and that we know we're counting all of the molecules that are present. Now, of course, HC3N is not a light bulb, right? A molecule is not a light bulb because it gives off light at discrete frequencies. The energies in molecules, these very small objects, is quantized. So when you consider rotational transitions, this means that molecules are spinning with fixed values of angular momentum, and they absorb and emit photons to move between these angular momentum space. Now, I like to think in some ways of molecules in space as not being, not having, they're lazy. I have to say a little bit. They're fundamentally lazy. Once a molecule in space starts spinning or dancing, it really just wants to stop. It really just wants to stop and give off a photon and move back down to its lowest energy state. All right? So we're sort of constantly collecting all of these photons that are coming about from molecules that are spinning and then slowing down. So observing different transitions of a molecule then gives you insight into the fraction of the molecules that have each of these energies, the amount of gas that corresponds to each of these different energy or excitation states. Now, this is a map of HC3N, the molecule of 4 different transitions across the entire galaxy center. We're going to focus initially on just one cloud for which we have even more transitions than this, some spectra and even more energies. But first we want to say, okay, so we know that our molecule is going to have different energies give off different colored photons. Where are they getting this energy from, right? What is fundamentally setting this distribution of energies? So remember, as we said, HC3N is far from being the most common molecule in a cloud, right? For every one of these molecules, you're gonna see about 1 billion molecules that are H2. And so as our HC3N molecule moves around the cloud, it's going to be encountering or colliding with all of the surrounding H2 molecules. And when it does that, a collision will bump it up, make it spin faster to higher energy state. It wants to stop, it gives off a photon. Now, depending on how many molecules are around, there's a possibility it has a couple of these collisions, a couple of these encounters. So it's spinning very fast before it has a chance to actually give off a photon. And so what we can do, right, by actually counting up the number of photons that are coming from each of these energy distributions, the number of molecules at each energy state, that tells you something about how regularly the molecule is undergoing collisions. What's the statistical likelihood that it undergoes 1, 2, 3, 4 transitions before it can give off that photon, right? And this then tells you something fundamentally about the density of the gas. So when we look at this cloud that we've chosen in the center of our galaxy, and we look at the data that we've taken, what we actually see is a little bit more complicated. Our curve here has 2 peaks, and so what we see are 2 different density components. So we see one that's low excitation. So this tells us that the molecule in this gas has not experienced so many collisions, meaning it's in low density gas. And there's another peak here that's coming from highly excited molecules that have undergone a lot of collisions and so are experiencing higher density gas. And we can go even further and compare the amount of gas in each of these density components, the amount of gas that has a density of a few thousand molecules per cubic centimeter, the amount of gas that has 100,000 molecules per cubic centimeter. We see that about 15% of the gas is in this high density component. So we're still really dominated by the lower density gas, but this high density gas is present, right? So we want to take this, what we're able to learn from this one cloud, for which we can look at a lot of different transitions of the HC3N molecule, and we want to apply this back to the whole galaxy center to say something about how density is evolving spatially now among all the clouds that we're looking at. And so to do this, we're going to use this to inform choosing 2 representative transitions. One transition, which is going to tell us approximately how much low density gas is present. And one transition which is going to be representative of the amount of high density gas. And now we can go back to our gorgeous maps of HC3N across the entire galaxy center, and we can make a nice ratio map of the amount of this low density gas tracer, lower density tracer compared to the higher density tracer. So what I want you to notice in this ratio map is that there's a shift as you go from left to right, from dark colors, which represent low ratios, so a relatively small amount of that high density gas, to lighter colors that mean that there's a larger amount of high density gas. And this increase happens at a radius of around 350 light years as gas is entering the galactic center. This is the radius at which we expect that the gas that has been shocked on larger orbits in the bar is sort of first encountering and first becoming part of the central regions of our galaxy. So we can go further, right? So we can say, okay, so this is something that tells us already that there's a change as we get into the galaxy center, and we can start to quantify this change, much more dense gas. But now we can go in and ask, well, what's happening if you get very close to the black hole? How does the density change? And so remember here, basically all of the gas we saw in the previous map is gas that's at least 300 light years away from the black hole. So now if we go in very close to the circumnuclear disk, gas within 10 light years of the black hole, again, you see evidence of at least sort of two density components, but both of these are much higher. So you see evidence that there is a larger fraction of dense gas, and the gas in this region is in fact itself just much denser than gas further out in the galaxy center. So the trend is continuing, and as the gas gets closer to the black hole, we see the density is going up. And that is not all that is going up. We also can see that the amount of hot gas is increasing as you go closer to the black hole. And to do this, we look directly at the H2 molecule, which you cannot always do. It's a little bit tricky, but luckily the gas in the galaxy center is simply so hot that we are able to see it directly. And we can use this to model the amount of gas that we see at each temperature, and we model it as a power law. So we basically say the amount of gas at one temperature is proportional to temperature to some exponent. And so we can look at gas, again, this is the gas far away from the black hole at 300 light years. What you see is a power law index that is large. In this case, large means relatively steep. It means that you have a large amount of cool gas, a relatively small amount of hot gas. But when you get close in, when you get into the gas that is now in the circumnuclear disk within 10 light years, what you see is a much smaller power law index. This is indicating a much flatter distribution of temperatures. You have much more hot gas compared to the amount of cooler gas that is present. So not only is there more warm gas closer to the black hole, the study also showed that the heating that we see in this gas is consistent with expectations for shocks. The shocks are what is heating this gas, and this is implying that the gas closer in has experienced more and stronger shocks than gas further out. This matches also what we see from the turbulent line widths. So we see larger line widths as well, very close into the black hole. These are consistent with larger shock velocities. And taken all together, what this starts to suggest is the gas in the center of our galaxy is most strongly affected by the shocks that it experiences as it moves inward. And in fact, the most important thing, despite the fact that there is a lot of UV radiation, there's a lot of cosmic rays, the shocks from simply funneling gas into the center of our galaxy seem to be one of the biggest factors in making the properties of the gas in the center of our galaxy more extreme than the disk. So from this we can say, okay, so in the Milky Way, it seems like this journey has some importance. But what we have to ask now is this a universally important conclusion? Right. So if inflow processes like this are most important for setting conditions in our own Milky Way center, can we actually broadly apply such a conclusion to other galaxy centers? And so we have to ask, what is happening in more extreme galaxy centers? And here I'm being a little bit mean, because as much as I love the center of our galaxy and think it is amazing, in some respects, there's not actually that much happening here. So on a cosmic scale, right? Although we know that the center of our galaxy was not always so quiet, it has built up a 4 million solar mass black hole. When we look at gamma rays, we see these enormous lobes, fossil outflow telling us that there's been past AGN or maybe starburst activity as recently as 10 million years ago. So this is all to say the galactic center wasn't always boring, but it kind of is right now, right? It's not doing much. So if you compare the black hole, right? So how bright does our black hole get from accretion on it to the range of luminosities you might more typically see in an AGN, an actively accreting black hole? Our black hole is off the charts, but it is off the charts in the wrong direction. It is 7 to 8 orders of magnitude lower than the luminosities you would see in a typical AGN. And we can even go back through the power of science to ask what's it been doing for the past few hundred years. So this even allows for recent activity that we can detect from X-ray light coming from past outbursts that reflects off of clouds in the galaxy center just a few hundred light years from the black hole, and then comes to our telescopes just a few hundred light years later than the light from the explosion would. And so we can see that within the past few hundred years, our black hole has been more active. Still nothing that you would really call, however, an AGN. And you can also ask about the star formation, right? And the star formation isn't much to speak of, but compared to the sample of AGN, it registers, right? We've got a star formation rate that is not totally puny. But if you look outside of the sample to some of the most impressive starbursts we see in the nearby universe, for example, ARB-220, which is forming stars at a rate of 200 solar masses per year, that makes the 10th of a solar mass per year that we manage to eke out in the central kiloparsec of our galaxy really just peanuts. But the problem has been historically that these other galaxies, if you want to find a galaxy that's more active than ours, you have to go at least 400 times further away. At least 10 million light years away, so much further than the center of our galaxy. And we haven't really been able to examine the centers of these galaxies with the same resolution that we've been able to use to probe the center of our own galaxy. But we've been extremely lucky in the past few years that our tools are getting better. And what we have now is we have access to ALMA, an interferometer of dishes up in the Chilean high desert. And we can now start looking at the centers of other galaxies with sub-light year resolution. This is totally unprecedented. It's more than 100 times better than we were able to achieve with previous telescopes. So where can we go with ALMA? One place we can go is NGC 253. This is a starburst galaxy that in many ways is very similar to the Milky Way. So it's a barred spiral galaxy, it has a very similar total mass to the Milky Way, maybe even a comparable black hole mass. What is different is that it is forming stars like gangbusters, right? So this is a galaxy that's forming at least 40 times more stars in its central regions. Like our galaxy, it doesn't seem to have an active black hole, however, but what it does have that our galaxy lacks is a huge outflow. So all of this star formation is driving a massive molecular outflow that we can detect and have detected with ALMA. This thing is putting out 30 solar masses of gas just every year, ejecting it from the center of our galaxy. And the amount of mass that this outflow over its lifetime has ejected from the center of NGC 253, it has thrown more mass out of the center of this galaxy than we even have today in the center of our own galaxy, right? This is a phenomenal, huge outflow that is greatly shaping what's going on in this galaxy. Now looking closer in, because that's what we like to do and that's what ALMA is all about. So once again, we can zoom in toward the central regions, and once again, you can see that we sure can pick them, right? So even though we don't live inside of this galaxy, it so happens we again have to look at it edge on. And now we're looking at Hubble's view of this galaxy and zooming into what Hubble had been able to see. So resolving the stars, and in fact, each of these blobs is not an individual stars, but each one of these is a superstar cluster, right? And so with Hubble, we were able to see that we have some superstar clusters that are present, but because of all of the gas and dust that's in the way, it has taken ALMA to actually pierce through this and see that in fact what Hubble was missing was more than a dozen of embedded young, massive superstar clusters currently forming in the very center of this galaxy. And when you put all of these together, you see that here indeed is enough star formation to power the outflow that we observe coming out. And again, the resolution of this image is amazing, right? It's less than 10 light years, less than 3 parsecs. So this is beautiful. But ALMA, of course, doesn't just show us the ionized gas. ALMA's sweet spot is really looking at the molecular gas. And so here you can see now we're transitioning to look at a dense gas tracer. So this is emission from HCN. This is a tracer of the dense gas. You can see, for example, knots of this gas in which these forming massive clusters are still embedded. We can keep going and look also at the more diffuse molecular gas, the incredibly extended gas that's coming from carbon monoxide, some of which is involved and entrained in this outflow that is coming out. And what we can do now is we can bring this back closer to home, and we can look at the CO emission. We can compare the gas properties in sort of a lovely apples to apples comparison, right? Same line of CO, same resolution, two different galaxies, one of them 10 million light years away. And what we see when we compare the gas properties is we see that in the center of this galaxy with its active starburst, right, we see elevated turbulence on all of the spatial scales that are probed here. It is simply more turbulent. And we can get into what the origin of these larger line widths might be by looking at the relationship we would expect between the line width coefficient, this is our y-axis, sigma squared over r, and the column density, the amount of gas. So if the gas is all self-gravitating, if it's in virial equilibrium, it should hang out somewhere near this green line. And you see this is mostly consistent for gas in our galaxy center. Almost all of the gas in our galaxy center is found in gravitationally bound cloud structures. But in NGC 253 and these orange points, right, what we see is that only the highest column density gas is actually consistent with being bound to the clouds. So this tells us that we have a scenario going on here where we may be seeing the feedback from the clusters injecting energy that's leading to transient structure and even unbinding the gas. So with AAMA, we have many other galaxy centers that we're able to put into focus, right? Not just one, but we are able to look at a number of different nearby galaxies, all of which we can resolve now as sort of gorgeous few light year resolution. And this gives us rich possibilities. So we can use the quiescent galaxy center, our Milky Way center, as a control and isolate the impact that these different feedback variables have on the gas property. Actually trying to say what happens if you have just star formation or just an AGN, or what happens if you put all of these together. And so I want to leave you at the end of this talk here with the message that this is a time of excitement. So the center of our galaxy no longer has to be this sample size of one from which we try to draw conclusions. So now that we have these nearby galaxies within reach, we can start to place the center of our galaxy in its true context and understand both what it can and perhaps even more importantly, what it cannot teach us about the physics that governs the evolution of galaxy nuclei.
Thank you so much, Betsy, for taking us on this amazing journey to this exotic location. I just want to remind the participants that you can type questions into the Q&A, and we have some help from the AAS Executive Office. Elisabeth Sculderi is going to read our first question. Take it away, Elisabeth.
Greetings, everyone. The first comment is not a question. I just want to read that Robert Nukuta thanked Elisabeth for the moment's silence. Then I have a question from Mordecai Mark Maclow. Is the shift in density shown by HC3N symmetric around the center?
So that is a great question. So the data set that we had to probe it is not symmetric around the center, and that is largely because the distribution of gas in the center of our galaxy is not symmetric. The majority of the gas is on that left-hand or eastern side. It would be lovely, and I think it would be a wonderful future study to actually try to go and map some of the gas that's further on the other side. I think there are some galaxy plane surveys that would let us do it to actually see to what extent, right, this is in fact a symmetric phenomenon.
Thank you. The next question I have is from Sanskriti Das. How hot, sorry, the screen moves around a bit. How hot is the gas probe by radio? Also, at what wavelength is it?
So it depends a little bit because radio, you can see a lot of things. So you see ionized gas that can be a few thousand Kelvin, sort of like 6,000 to 8,000 Kelvin. One of the main probes I use is the ammonia molecule. And so here now you're looking at the molecular gas, and you see these temperatures, these sort of characteristic temperatures of anywhere from 30 Kelvin up to 300 or more Kelvin. In fact, when you look at some of the gas you can directly probe with H2, you start to get into temperatures of even a few thousand Kelvin.
Thank you. The next question I have is from Yuan Chuan Zhu. Are the gases in thermal equilibrium, as it seems you can measure the temperature T?
Yeah, so you have to be careful of your tracer. So as long as you are using a tracer that is sufficiently thermalized, like ammonia, we do expect that it is largely in thermal equilibrium. You can get around this a little bit again by directly observing H2, right? And if you measure H2, like H2 is in thermal equilibrium with itself, it seems. So you can directly measure temperatures that way, although you're limited, you're not able to measure the coolest temperatures that are present using H2. But you do have to be very careful. So we don't use some of these larger molecules like HCN or HC3N to measure temperatures because they are not thermalized.
Thank you. The next question I have is from Patricia Kisnick. Sorry, Pat, I know how to say your last name. How do magnetic fields come into the scenario you presented?
So this is a really interesting question. I think this is something that has not been yet thought a lot about or modeled in terms of the inflow of gas and the motions of gas. It's very likely that these have a very important role when it comes to the star formation and regulating the star formation, because we do have evidence that the magnetic fields of the gas in the central regions of our galaxy, just like all of the other properties, the magnetic fields are stronger in this region. And this could tend, for example, to inhibit or at the very least sort of moderate and be a very important moderating factor in the collapse as well as the pressures, right, that hold structures up in this region.
All right, the next question I have is from Farhad Zeda. What is responsible producing shocks given that star formation is not prevalent? Shocks will have a tough time to penetrate deep inside dense clouds lying in the galactic center. Cosmic ray heating is not a surface effect and can easily heat dense gas clouds.
Yeah, so I would argue, I mean, I think as to what is primarily responsible, right? I mean, I think that that's still a little bit of an open question of what is driving the turbulence on the larger scales. There have been suggestions that acoustic instabilities might be responsible, as well as recent work that suggests maybe that is not actually the primary factor. As far as shocks penetrating deep inside, I think we're starting to have some really lovely observations also with ALMA that are actually looking at the molecular gas with dense gas tracers on very small size scales. And for the most part, it appears that the turbulence, the increased and enhanced turbulence, really is persisting into the dense gas tracers, into the centers of these clouds. So while the shock itself, the outer shock, may not necessarily go all the way inside of the cloud, you're going to have extreme turbulent motions and potentially other shocks that are occurring as the turbulence dissipates inside of the clouds.
Okay, from Stephen Spangler, what do we know about the spectral types of the stars in the central cluster? Do we know what the spectral type and luminosity class of S2 is?
So I don't know that off the top of my head. I believe that most of the stars in the central cluster, I mean, it's a big mix because we have a nuclear star cluster, and that means that there's a very old and metal poor population, as well as a young population that has an age of less than 10 million years. Professor Jessica Liu at the University of Hawaii, Tuan Do at UCLA are both quite experts in this region. I believe that many of these stars are B-type stars, of the stars that we actually use to probe the motion and detect use their orbits to measure the properties of the black hole. But this is a little bit outside of my area, so I absolutely recommend looking at work by those two folks.
Okay, from Ursimo, I have, hello. Wanted to ask why we don't study Andromeda as it is being a huge nearby galaxy.
So I'm a little bit biased in this talk. We absolutely do study Andromeda. Andromeda is unfortunately, I mean, fortunately for us because we can see it in the sky, but unfortunately a northern hemisphere source. And so the ALMA telescope is only in Chile, so it really is only accessing, you know, the southern hemisphere sky. We do have some millimeter interferometers like NOIMA in the northern hemisphere. And so people definitely do study Andromeda. They also study other galaxies like M82 that are really exciting. Andromeda is actually a little bit gas poor in its center, however. So if you really wanted to look at molecular gas in its center, you don't see so much compared to our galaxy.
Okay, the next question I have is from Stephen Koch. Amazing talk, thank you. You mentioned the bulge, SMBH relation. Could you comment on why this relation breaks down for bulgeness? Simple disk galaxies, in parentheses, flat galaxies, which are found to host SMBH is as well.
So this is a great question, which again is unfortunately a little bit outside of my expertise. What we see is that galaxies in general, and I don't want to say too much, but galaxies, for example, in our local group, like M33, right? This is a spiral galaxy that does not have a bulge. It also does not have that we can detect anything that is supermassive or even intermediate mass black hole at its center. So it seems like there's something about the processes that build up a black hole and or the impact of a black hole, right, that leads to a bulge. Where you see one, you see the other, to my understanding of the literature, and where you don't see one, you don't expect to see the other.
So thank you, Elisabeth.
I apologize. I'm repeating this question again. I don't know much about disk galaxies which do host supermassive black holes, but don't have a bulge. I believe they're outliers to the relation, but this is not my area.
Okay, so thank you, Elisabeth and Elisabeth, for this wonderful session. And to everyone else, there's still a lot going on this evening. We have the evening poster session coming up. We have webinars, we have workshops, we have meet and greets. So please enjoy the rest of your day, and we'll see you back at the plenary tomorrow morning. Thank you very much.